Thanks a lot, David, and also thanks everyone for being here, and to the previous speakers for all the nice introductions. It makes it much easier. I'd like to study very similar topics as we heard about, but a bit more from a practical example. And so it'll be a bit technical on the side of LLMs, also what it means for them to be open, we already heard. And then I'd like to give the concrete example of medical LLMs, which I think is a very interesting domain where there can be surprising results, I would say. Okay, so I guess you already know, most of you, what are actually LLMs. I'll just spend maybe 1 minute on it. It's just fascinating how they actually work and how simple they are, in the sense that they're really just predicting the next word. So it's really a standard prediction problem, which we solve by an artificial neural network, which just sees the word so far and predicts the next word. And there's so much text available in the world that we have so much signal that we can learn from to actually set the weights in this neural network, which is really just a standard neural network. There's nothing special about it. So on the bottom, you can see the input to the network, which is the few words we have seen so far. So just the words which are present, you put a 1, otherwise you put a 0. And on the top, you see the output of the neural network, which is trained to be correct as the next word, which is the green one here. And you're saying, maybe I'm simplifying here a bit, but I'm not, because actually even the transformer architecture is really just that. The transformer is just maybe a subset of the black connections that you see here between all these nodes, right? Just a slightly more efficient subset of these weights, so that you have an efficiency gain in training and in using the model, that you don't need to have the all n squared many connections. So what happened? So maybe similar thing happened already maybe 10 years ago, where we had just a capacity jump in traditional deep learning, where we had just image classification and accuracy improved. The error rate got cut in half in 2012, which is one of these blue bars here, the error rate became much lower suddenly when deep learning became kind of practical, despite the fact that it was already conceptually there for many, many decades before, but then started to work. So then ChatGPT, a similar thing happened again. We had a similar kind of accuracy increase, you could say, from predicting this next word, as I showed you. It's just slightly more accurate now than it used to be. So what's different? So, I mean, what's really shocking to me, at least, is the breadth of this capability, right? So that just by this fact that you can predict the next word, there's like so much that now you can do, which was completely impossible just a year ago. So every task that can be formulated in language, and language is so universal, right? Everything we do as humans can basically be formulated in language, therefore can, to a surprisingly good accuracy, also be solved by these models, right? And that's really what makes this so different this time, and still surprised like how fast this is going, and how I think it's kind of unprecedented that the technology has an impact so quickly, right? That just a year ago was not there, and now is there, even if it's conceptually was clear what it is, but already affecting all of us, I would say, in our professional life, maybe even private. So how that many contact points where we actually are affected by large language models because they work so well. Okay, what can we do? So it's important to understand this technology, and for that it's also nice to actually study it and build it yourself. And it's really nice that in kind of 300 lines of open source code you can start playing, you can start training your own language model to speak a decent quality of English with just one GPU. It's actually surprising. So if you just train 3-4 hours on a single GPU, you can have a decent English-speaking model. So it's not completely out of reach to have a small example of this technology. And then if you go the same thing on a larger scale, so actually we really use the same code base as that, we also use that on larger scales, then you can train on all public data. As we heard, there's plenty of public data available. So you get a really strong increase in capabilities for that. You can do other things. You can run data-sensitive applications. For that, I think it's very important that you also have the model on premise, like where the data actually is, to ensure nothing is leaked. And you can also think about maybe domain-specific models, like, for example, for the health domain, or I don't know, maybe biomedical data and so on, and I will come back to this as one particular example. Okay, so the way to train these models is very standard, right? It's nothing special, just like it has always been in traditional machine learning. You have training data, you train the model that's on the left here, and there's maybe a second stage of training, which would be the fine-tuning or alignment phase, where you do a just same algorithm, same software. You do a little bit more training to actually learn particular capabilities, but actually most capabilities are coming from the base training, right? From the base model where you train on huge amounts of public data. And you need evaluation data to actually measure how your model works. Now, the problem is we don't have most of these data available when we have just commercial models. We talked about it a lot in previous sessions. So the reproducibility is just not there if we do not have this training data. So for this to be reproducible and transparent, we need the data, we need the code, and we also need the model, of course, but that's already been said. And if we have all these three, then we have a reproducible pipeline. And I think this is really crucial for several reasons, right? From a scientist perspective, you would just state that, okay, if someone claims something about these are the capabilities of these models, or these are the limitations and so on, so you would like to be sure, right? You would like to be able to reproduce this, and as it's a key technology, I think this is very important to be able to study this technology. And there's many other reasons, also from a commercial point of view. Of course, we heard it, some people prefer open source software, some people have commercial software they prefer, depending on what your company wants to do. Even in traditional software, we have a productive coexistence of like commercial, for example, open operating systems like Windows and Mac, and we have open source systems which are Linux, and you can see they're both used. It's not black and white that one of them is immediately disappearing, or it really depends on the use case. But for critical applications, for example, such as healthcare, I would advocate that this is really the way to go to actually understand what went into the model building, how the sausage was made. So what's the situation now? We have a lot of good models, right? You hear it in the news every week. The commercial new models get released, but actually it's surprising. The gap is not so big. The gap between open source models and commercial ones is surprisingly small. So we heard it from Leandro, right? So there was the story of the AI winter, right? It used to take decades when AI didn't work, and then it's worked again, and then there was a winter and spring again, and now it's aligned with the actual seasons of the year. So, as we mentioned, there was a bit of a winter just the last few months, and now it's spring again that we see that, okay, more models do get actually made open source, and so here they are ranked by the leaderboard, like what's your winning rate against another model on a really new question that has not been seen before, right? Because evaluation of these models is very tricky. But this OpenLLM leaderboard, I just got this yesterday from the website, is quite a nice way, because users actually provide questions, which then you can ensure they have not been seen in the training set, and you see just which answer do you like more of the two models. So that's a way to evaluate them. They are coming with different licenses, which is another story which we talked about. Maybe the most liberal license here would be from Mistral, the Apache 2 license, which is similar as the MIT license. And then maybe the most used model now is models based on Llama 2, which is like the wizard LLM you have on the 13th row or so, where you're also allowed to use this model for basically anything you like. But if more than 500 million people would use it, you have to pay some fee, but still quite a liberal license. Okay, so this is kind of hopeful, but it's also interesting what's going to happen with this gap between closed models and open models. And as we were already saying, so there's this openness in the weights, which is just a minimal kind of openness, which is used a lot these days to build new applications. But we would really like to go to the bottom row here, that we also have a full reproducibility and transparency, what has went into the pre-training, what has went into the alignment, and so on. So here, current models are around like Olmo and like StarCoder, we heard, and Bloom as well. So these are, it's a much smaller crop of models which have this, which check this transparency requirement, right? Okay, so what to do? So I think there's really a huge opportunity to crowdsource this a bit more, because it's just so important, right? It's not just the alignment phase, it's not just the fine-tuning which is critical, right? Because most of the capabilities of these models come from the base model on the left. So from these public, huge data sets they've been trained on, or actually some secret mix between public and non-public data. So most of it is a web crawl, right? And so it's quite interesting to understand like how is a web crawl processed, or the code data set, like, well, how do we process this? Which data documents do we keep and which not? When we do a web crawl, can we train on the New York Times or not, right? So all these questions, so many decisions get made. And my point here is kind of who makes these decisions is quite important, right? And to be transparent about these decisions made, right? Because if it's made by just a company in the closed and then they just release the model, but not how they made the training data, it's just going to be so difficult to understand if all aspects of the model or potential risks or that might come from this model if you really have no idea on the process, on what was decided to go into the training data or not, which could include harmful data, which could include all kinds of illegal data and so on. There is a really nice project which I was not involved, which is called Open Assistant, which did exactly that, which just democratized the question on how to build a fine-tuning data set. So, and also it's nice because this was made completely multilingual to ask a lot of people on the web, volunteers, just provide us some questions and then rank the answers of these LLMs. The data set is made completely available, so we can inspect it, we can study it for risks, and we can make sure people are represented, right, that each languages are represented and values are represented, because we can look at what is there and who made it and why was it deleted or not deleted. So I think that's an opportunity. And in the last 2 minutes, I just have this concrete example of something we try to do with students here at DPFL. We just, there was a time where the new cluster was only setting up, so it was not completely ready yet, and they told us we can use 100 of the GPUs for a month, basically, so we had to be very careful to use it in exactly that time frame, because afterwards it was not available anymore. And it was not a huge cluster, right? Even with 100 GPUs for 2 weeks, you can actually do very, very nice things with large language models. So what we did here is just to take medical literature, and we only took publicly available papers and made fully transparent which papers we took. We also took medical guidelines from medical organizations, which are also publicly available, and they're also verified by doctors, and so it's kind of nice that you can make transparent what you trained on. We trained for 2 weeks, and we obtained a very well-performing large language model. So the first problem we had is that there was no distributed trainer available in the open source, but there was many proprietary ones. But we then went ahead. This was like summer last year, and everything was done completely in the public, that we just tried to make the necessary modification to allow the distributed training for Llama 2 based models, for example. And that's also been quite useful, and other people have picked it up since then, and everyone can use this for fine-tuning and also for pre-training if you're interested. Then we trained on 50 billion tokens from these papers. And so most of them were from entire papers, like from the PDFs, was already extracted. Sometimes it took a lot of work to actually process this data and identify the right data sources. But it ended up to be the best performing open source or open model medical model. So maybe I show the results here. It performed almost as good as the Meditron 2 by Google, which has 500 billion parameters, and this one only has 70 billion. So it performed also much better than like Llama 2 originally, and this was nice. We also managed to do a multimodal version where we can also use images, but there we only did the 7 billion model to allow it to read images and text, where it also performs really well. And of course, it's risky to, we're not going to give advice for people to directly use this for medical advice, right? So we have to very properly evaluate this also by medical doctors, which is what we started to do and what we also keep doing and make this more systematic. And actually, I think this is a great use case, right, for the open community to play this role of evaluation, right, to make sure that let's say the global community of doctors can look and compare all available large language models, like commercial or not, and really find risks and limitations of these models and measure their failure modes to be sure that these models are safe and that we can compare them, and for that it's just so important to have this transparency, both for the evaluation but also for the training side of these models. Yes, this was a very nice student project, and yeah, it's just cool to work in an interdisciplinary team, less some people trying the data, cleaning the data, training the model, doing the evals, so students love this, and it's nice to practically build some things. Okay, I should wrap up. This was already mentioned before, we also have the Swiss AI initiative coming up, so in a few months, 1 or 2, these GPUs in Lugano should become available, which were already ordered several years ago, but it's just perfect timing to now have actually the needed resources for doing research on large language model, because it is something that we need to team up, as was already mentioned, because the resource costs are intensive. So again, this is a great opportunity to get everyone on board. So please join us, help us to evaluate these models, help us to build these models, study them, and in this feedback loop, make sure we can understand this technology better and contribute to the openness and trustworthiness of this technology in the next few years. So thank you, and happy to take any question.